Hi, my name is Dev, and today I'm going to talk to you about our work on analysis and workload characterization of the CERN EOS storage system. Researchers need access to traces and logs of large-scale systems to really understand the data flow and internal workings of such systems. Unfortunately, such analysis is hard to come by. There's not many public trace analysis studies out there. Further, studies that are out there focus on single systems, but what we really need is a cross-system comparison so that we can figure out what trends are system-specific and what apply to wider, large-scale systems. We motivate the need for public repositories of traces and uniform trace formats that will further simplify such comparison. In this work, we looked at the CERN EOS file system traces. These span roughly 11 months, capturing over 2.4 billion events in production at the CERN EOS file system. We look at conventional wisdom, such that automated migrations make up most of the data activity and write-once read-only paradigm, and we validate it with new data. We also compare our analysis to two other systems, NCAR and ECMWF, from studies in the past, and compare and contrast. Finally, we reflect on the trace formats of these three systems and motivate the need for uniform formats and tools. Our data is between 2016 and 2017 at CERN. We also looked at past analysis such as NCAR and ECMWF. Our data is much larger than these systems. Our data captures 10 times as many events of either of these systems and is much larger in scale. The EOS file system at CERN is shared by 4 experiments. Our data comes from the CMS experiment in particular. This is roughly how the file system looks. You had 3 pools of data. Users only interact with the analysis pool in a POSIX-like fashion. Data is directly stored on the archive pool or the tape pool and only fetched to the analysis pool on user request for processing. As you can imagine, a lot of data movement happens in this system. We present a number of observations, of which I will talk about 3 today in the interest of time. We look at how file system metadata can inform us about file activity. We look at the conventional wisdom that automated migrations make up most of the activity, but in our system, they are different. We also look at write-once read-maybe paradigm and how it is different in the CERN system. We start with file activity. Files that are below 64 megabytes, small files, make up most of the files by number in the CERN EOS file system. However, while they make up 75% of all the files, they make up less than 5% of the stored data volume. On the other hand, you have 12 256 terabyte files that are backup files, that make up 22% of all the data stored by volume. Both these sets of files will benefit from dedicated strategies for caching and storage. In general, what we see is that larger files make up a greater share of the volume than NCAR or ECMWF, meaning that there are many large files that occupy large amounts of stored space in the CERN data. We believe this is due to the difference in nature of particulate and atmospheric data, and also the difference between the time periods of when these studies were done. We further look at how user accounts can help inform us about file activity. We see that a very small number of users do not perform any reads, that is, they're write-only. At least half the users read more than 8 terabytes of data, while the top reader read 42% of all the reads that we saw. On the other hand, for writes, 40% of user accounts do not contribute any writes at all. They are essentially read-only users. Of the remaining, about half write at least 16 gigabytes, which is again smaller in scale than the amount that most accounts read. We find that writes are dominated by a small number of accounts, just 5 user accounts, mainly related to moving data around, perform 95% of the writes. You will see that almost all the data written is by the top 5% of the 1800 accounts that we observe. For reads, it's about 90%. Further, we divide these accounts into system accounts that are automated and user accounts that are user triggered. And we see that, unlike other systems, data movement still makes up a lot of the activity, but now it's a lot more user triggered rather than automated. You will see that user actions are almost 10 times the total actions performed by automated systems. They write much more data and read much more data than systems as well. Breaking it down, you will see that system applications pertain to replication, balancing, training, maintenance activities that roughly read and write the same amount of data as they're moving it around. On the other hand, user-initiated copy utilities that are specifically tagged wrote 38 petabytes and read 53 petabytes of data. Processing utilities were responsible for 7.4 petabytes and 2.8 petabytes of writes and reads respectively. There's a lot of untagged reads and writes which do not specify application, but most of these are either processing scripts or copying scripts. As you can see, data movement still dominates the read and write in the system. But in this case, it is user accounts triggering it rather than system accounts or automated activities triggering it, since data of interest is fetched to the analysis pool and acted upon. Then we look at write once, read maybe, which has been conventional wisdom in systems for ages. It is slightly different in the CERN EOS system. Read maybe is not as applicable as only the data of interest is fetched into the analysis pool. So most files see reads. As you will see in the graph, 42% of files are read a second time, 12% a third time, and so on. It's a heavy-tailed Zipfian distribution. Writes, on the other hand, only happen once. Rewrites or updates are rare. A second write is extremely unlikely. Only a few hundred out of millions of files were written to a second time. Third time is even less likely, and so on. So while the write once, read maybe paradigm holds, it's important to calibrate your view to the subsystem you're analyzing, because read is much more likely than read maybe may suggest for our system. We looked at 3 different trace formats, and all of them vary in the data that they capture. CERN captures deltas, NCAR captures specific actions that happened, and ECMWF includes snapshots. One-to-one comparison of these things is not always easy. For example, a file size going to 0 can be inferred as a delete action in CERN, while NCAR will have a specific delete action. It's important that we are able to compare these traces one-to-one to really understand how these systems work and the larger trends in them. We motivate the need for a uniform format of traces and uniform tools that can allow easy cross-comparison. They will also allow us better insights over time as we look at traces from different time periods and different scales of systems. We also motivate the need for a public repository of traces. Only 3 such analyses have been done in the past decade. We need more data. In conclusion, in this paper we talked about the CERN EOS file system and how its workload looks. We looked at trends in large-scale scientific archives from the perspective of the CERN EOS system and how it validates conventional wisdom and findings in the past. We also want to use this platform to call for action. If you are in an institution or a lab that has large-scale archives or large-scale systems, we want you to help us set up public repositories of such trace data that researchers can better utilize to understand, optimize, and design large-scale systems. We need studies into better anonymization of data due to legal issues for industries to share data. We also need studies on simulation of trace data so that companies that don't want to share their specific data can share a workload that looks a lot like their data. Finally, we want to work on uniform formats for such analysis, tools that will allow you to easily plug in multiple traces and quickly generate insights. All the data that we presented is open source and available on the GitHub repository mentioned. We would like to thank our contact at CERN, Dr. Dirk Dulman, for getting us access to these traces, and all my collaborators at UC Santa Cruz, and the reviewers of the paper for their feedback. I would like to thank you for listening to this talk, and feel free to ask any questions. Thanks.